All right. Good morning, everyone. So welcome back to C69. Today we're going to talk about multi-threading. As I talk about that, what I hope is that by now you are actually familiar with the project. You have started to work on Pintos. And at least you have watched the 2 videos I gave you. You have audio set up. You try to reproduce actually what I have done in the video. And by now, if you have looked at the code and so on, you should kind of understand a little bit about multi-threading, okay? But again, and that's going to help you actually follow what I'm going to do today, because what I'm going to do today is actually directly related to your project one, okay? So let's start with multi-threading. So we talked a little bit about multi-threading last time already. That was just a brief introduction, but now let's go into more detail. So first of all, I'm going to try to disambiguate things here, okay? Or maybe actually keep it ambiguous a little bit. If you have read the textbook talks about process, and they talk about managing multi-process running concurrently, right? But if you look at Pintos doesn't have process, okay? Pintos, if you read the documentation, they talk about kernel threads, okay? But also, if you look at what you have done in BO9, you talk about threads as well, but they were not kernel threads. They were something we call user threads, right? So maybe all of that is kind of confusing. Let's put it under the rug for now, okay? For now, let's simplify, okay? It's kind of it's not accurate, right? But for now, we're going to simplify. One process equal one thread, okay? And here I'm just going to talk about thread, okay? I'm going to talk about thread because I want to match what we see on Pintos, okay? So it's not exactly what you saw on the textbook. I'm trying a different approach here, but you will see it's kind of similar, right? But I'm going to talk about thread for now, and this is why I'm going to talk about multi-threading, okay? All right. Yet I want to make a distinction between a program and a thread. Okay, so what's a program? Well, it's some static data on some storage, right? There's some kind of a binary code, and this code is stored in a file that is on the disk, right? So that's really a program. A thread is an instance of a program execution. Okay, so of course you can have multiple threads running the same program, basically. Okay. So that's the idea. And here we're going to look at, it's really like threads are re-executed at the end. I mean, threads are actually run by the CPU, and those threads are run concurrently by the CPU, okay, by our OS actually, okay. All right, so that's what we're going to look at. Remember, I introduced that the last week, okay. So this is kind of our simplified architecture. We have a CPU, we have a memory, and again, memory is not only the RAM, it's actually the RAM plus the I/O, input, output, and so on and so forth, right? But all of that is kind of the memory address space. And the CPU here, what it does, it's like it executes instructions, okay? So that's what a CPU does all the time, okay? It executes instructions, and for that, it has a special register, a pointer that we call the EIP, which is instruction pointer that points to the instruction to execute next, right? And then actually you increment +1 on the address, and then execute the next instructions, unless it's a jump or something like this, like a branching instruction. Okay, so it does that all the time. You will see we call that direct execution actually. It has something else which is called the stack pointer. Okay, and the stack pointer points into a place in memory where we're going to store variables, we're going to store function calls, we're going to store a bunch of things. So of course, the CPU executes one program at a time. So at a given time, the instruction pointer points, of course, to the code for that thread. Okay, so here, for example, thread B, and of course, it points to the stack for that thread, right? But of course, we have seen that, at some point it's going to switch to another program. And so we're going to change the instruction pointer. We're going to change the stack pointer to point to thread A. But as I told you, a CPU will never stop, right? It will always execute instructions, and there is no such a thing as an instruction that says, stop and execute something else, right? What it uses is the concept of interrupt. Okay, and an interrupt is, as the name says, it's going to stop the CPU. It's going to interrupt the execution to notify of something happened. Okay, and we're going to go into more detail in this lecture. We saw that there was something interesting, which is the clock interrupt, because there is this idea of like every, we have a time quantum, and the time quantum is actually on Pinto's 100 milliseconds. Every 100 milliseconds, we're going to send actually an interrupt signal to the CPU, okay? And we're going to use that actually to schedule our threads and so on, okay? More later, but that's kind of what I introduced last time. So, the idea here is like we want to run all these threads concurrently, right? Kind of at the same time, okay? And the idea is like the CPU is going to run every thread a little bit of time and then switch to another one, and then execute it a little bit and then switch to another one, and so on and so forth, right? So in a way, the fact that a CPU kind of execute code and never stop, we call that direct execution, right? I mean, the CPU points directly to the program that is currently executing. And limited direct execution, because at some point, the CPU is going to be interrupted, is going to stop executing the thread, and then potentially, I mean, it depends what we do at the OS level, but here what we want is like to switch to another thread, okay? And we're going to call that context switching, okay? So here the CPU will switch to another thread when either the running thread yields the CPU, okay? And yield the CPU, it's not a special instruction actually. It's, the thread is somehow going to call the OS, okay? There's going to be an instruction, an API call if you want, or a special kind of function in the OS, and that function in the OS actually is going to do the context switch. Okay, so either the thread yields the CPU, or the CPU stops the running thread because there was a clock interrupt. Right, that's usually what happened. And so here the idea is like, because of these two things, the CPU is going to execute, a little bit of thread A and then thread B, and then, maybe actually go idle, okay? And idle is yet another process that do nothing, actually, basically. You see that in Pintos, there's the idle thread. And then go a little bit to thread B, and so on and so forth, right? And it's going to do that concurrently in a very fast pace, so that, I mean, this has a lot of advantages, okay? From the system perspective, we are better using the CPU, okay? So the CPU is like, maybe the most expensive stuff in our computer, and it's the faster thing also on our computer. And here we're using it to the best we can, right? By running multiple programs at the same time. From the user perspective, for us, using our laptop, for example, or our desktop, it looks like all the programs are executing at the same time, kind of in parallel, right? They are not executing in parallel, okay? They're executing one at a time, but because it goes fast, we have this impression that things are really going in parallel. I mean, right now, I'm streaming the video, I'm streaming the sound, I'm using the slides, and so on, and there are probably other programs running behind the scenes, and all of them are kind of, it looks like they're going in parallel, okay? But I mean, truly, they're actually concurrent. Right? They may go actually in parallel if I have, for example, a multi-core, actually it's the case, and they have really two programs running on two different cores. But again, I have more programs being executed concurrently that, of course, I have cores, right? So doing that actually requires mechanisms to manage and schedule those concurrents, right? Okay, and that's what we're going to look into more detail. So today's lectures, I'm going to start with interrupts, to understand a little bit how it works. Then we talk about this context switching, which is really actually about like, switching threads, okay, changing the current running thread. And then we talk about synchronization, because of course, when you're doing that, there's a kind of a new family of problems that arise, which is actually race conditions. Okay, so we're going to talk about synchronization. All right, so let's talk about interrupts first. What are interrupts? So first of all, there are two kinds of interrupts, okay? So there are one that we call external interrupt, okay? Some people call it hardware interrupt. Basically, it's like I/O devices, okay? And I/O devices, I mean, it means everything that is connected to your motherboard, basically, okay? So, every kind of course, external device that you have, the microphone here, my keyboard, my mouse, my screen, and so on, right? All of these are devices, the USB and stuff like that. There are stuff that are internal, okay, that I don't see, but the clock, there are, and others actually. And here the idea is like they use interrupt to tell the OS or to tell the system, say, hey, there's something happened. Okay, so for example, you first you do IO request. For example, hey, I want to read a key on the keyboard, and at some point a user pressed the key, and there we're going to see that later. But there's an interrupt sent to say, hey, now there is a key that's been pressed. Do something. Okay, or there is like there's something on the microphone. I've sampled some sound. Please, there is some data ready for you. Okay, so and so on and so forth. So these interrupts are actually used for the hardware to notify the system there is something that happened. There is some data ready. We have also internal interrupts. Okay, so what are internal interrupts? It's kind of weird. It's like interrupts that are generated by the running program. Okay. So it's not a hardware device. It's actually the program itself, the program that is currently running, that can generate interrupts. And you can generate two kinds of interrupts. Okay, one that we call fault. Okay, fault is like there is a problem. Okay, and the problem is like one problem that for example, is like divide by zero. Okay, what happens when you divide by zero? The CPU doesn't know how to divide by zero, and it's going to say, no, there's a problem here. I cannot complete this operation. So for that, actually, what it's going to do is like it's going to send an interrupt to itself. Okay, it's going to interrupt itself by sending a signal that says, "Hey, divide by zero." Okay, and we see that's a special interrupt. There are other kind of interrupts. Okay, we're going to see another one later in the semester, which is called page fault. Okay, we will see what's that. I'm not going to go into detail right now. But there are also interrupts that you can actually program. So you have actually instructions that are going to generate interrupts, and you will see that it's actually very useful, right? So it's kind of like, it's kind of weird. You're basically, it's a program, it generates an interrupt, so you're going to stop your execution in a way. The most famous one that you're going to see on project 2 actually is the system calls. Okay, we call it a system call trap, and it has a special number. I mean, you will see interrupts have numbers. On PTOS, it's like 30 in hexadecimal. On Linux, it's 80. But it's it's kind of a special interrupt that we're going to have when we're going to do system calls. Okay, again, more of that coming later. But the idea of like, programmatically, we can actually trigger an interrupt. So let's talk first about, let's look at first at external interrupt, right? So the naive kind of implementation, the naive view that you can have, and it's actually correct, right? It's naive, but it's correct. It's the following, right? So you have lines that comes to the CPU, okay? And the CPU knows that, this line is line 0, this line is line 1, this line is line 8, and so on. I say line because that's the name. We call it like interrupt request line. Those lines are, you can imagine it's really like, some kind of a physical, electric connection to the CPU. And if the device sends a signal on this electric thing, the CPU receives it and it's going to do something. It's like, hey, there is an interrupt that has been triggered. Okay. So that's how it works, right? And so in a way, I mean, this is the naive approach, but if you really implement it like that, it's actually not very practical, right? Why? Because first of all, it's hardwired, okay? And although actually, I mean, I'm going to argue that even if, the real implementation is actually not hardwired, but usually behind those RIQ lines are specific devices and they're always the same, okay? I mean, you will see. So they are hardwired. Also, the CPU might be interrupted all the time, right? What if you receive an interrupt, but then there's another interrupt and then another interrupt and so on and so forth. And the CPU is going to receive a lot of signals like that, okay? So that's why it's not great. You will see how we can handle that. Because the idea here is like, we want to have priority, right? The idea is that we're going to favor some device more than others, okay? We're going to say, no, some devices are more critical, okay, than others and so on. And we need to prioritize the interrupt that the CPU is receiving. Okay, so for example, here the clock is going to be more will have a higher priority than actually even the keyboard and so on, right? So the real implementation actually is like this, and we're going to use, on your motherboard you have these two actually devices, which is a programmable interrupt controller. Okay, so there are like small chipset, and actually the devices are connected to this chipset and not directly to the CPU. And what the CPU has, so here, so you see all the devices connected to the PIC, and actually here the CPU doesn't have multiple lines. Instead, it has one big line, but it's a vector, right? And here it's going to receive a signal which is 256 bits. Okay, so here you see that, and 256 bits. It means that you can actually kind of encode a lot of information, right? You can encode 2 to the power 256, so you can have a lot of kind of interrupt number, right? Okay, and so here we're going to connect our external, our devices to the PIC, and finally the PIC to the CPU. So these two devices, what they're going to do, they're going to manage the interrupts, right? When I receive an interrupt when they receive an interrupt signal, they're actually going to kind of like process it. It's very, very simple. They're going to process it, and at some point they're going to put an interrupt number here on the CPU vector, okay, on the CPU interrupt vector, okay. And the idea here is like those PIC devices can prioritize, okay, because you can have mask and so on. So what I can say is like, okay, I receive interrupt 0, okay, so I put interrupt 0, and because interrupt 0 has high priority, I'm going to mask the other interrupts, right, until the CPU has solved, until the CPU has handled the interrupts and is ready to handle a new interrupt, right? Or maybe you can have, something like, there is some kind of an interrupt, but then suddenly there is another interrupt that comes, and here we're going to interrupt the CPU again, just because the interrupt has higher priority. So basically here, the PIC are going to manage priority, and they will be able to mask, okay, they have this functionality to mask actually interrupts to prioritize actually what the CPU is doing. Okay, so some question on the chat. Why are some devices connected to the slave and the master? Why not connected all to the master? So the idea here is like that's a good question actually. So the idea is like to have a master that we will connect the ones that have high priority, okay, and the ones that are actually high priority are the clock, the keyboard. Okay, the keyboard is very important. Especially for the boot sequence and so on. So we're going to connect the clock and the keyboard and so on, and others. And the ones that are less priority, we put it on the slave. Why we are doing that? Because here, we can actually, you can have the master that kind of mask the entire the other devices. And also what we can create is like, so why having that? Because in the OS, this is maybe too much detail, but in the OS, we can have different kind of layers of the OS. We can have the OS that starts, which is like, the critical, when it boots and so on, and it's only going to use this one and shade the other one so that, this one is actually not managed right now, okay? And it's going to manage this one, and then provide the management of this other PIC to maybe higher level of the OS, right? So that's why they have this kind of cascading design. Other questions on modern system, are the PICs replaced with the south bridge? That's too much detail. I'm going to talk about that. But no. The south bridge is basically, I'm going to talk about that later. When we talk about virtualization, actually, I'm going to talk more about the architecture. But the south bridge is actually for the data, right? It's the bus that actually channels the data, right? This is kind of on the side. The interrupts are not channeling data, really. They're just channeling signals, interrupt signals. What's the difference between the real clock and the system clock? Well, you have two clocks on your system. One is like to keep track actually of the time, okay, the time that you have here, 11:30 and so on and so forth, and you can put timers and stuff like that. So it's kind of some kind of a device, right? But then you have the system clock, who actually is is used actually by the system to actually do the context switch and so on and so forth. But I mean, they work the same, right? It's at the end of the day, it's a quartz that kind of has an electric signal that is very regular and so on at a specific time interval. So they're the same, but we have two because we need two, one for the system to actually do the context switch and so on, and the other one just to have the time and so on, and used by other programs and stuff like that. Does your earlier statement about layers refers to security rings? Yes. Yeah. But again, I don't want to, okay, I don't want to kind of to digress too much, right? So right now let's focus just on like interrupts and multi-threading. Okay. All right. So this peak here, they are responsible basically to tell, you know, they're going to manage the interrupt, you know, and they're going to be the kind of the intermediary between the I/O devices and the CPU, right? Usually there is 16 lines of interrupt, of external interrupts, right? So RQ0 and RQ15. Okay, you can see that actually on your system. I will show you where. Interrupts have different priority, and usually, I mean, that was a default kind of x86 design. You know, RQ0 is the highest priority, and interrupt can be masked, right? So that's the idea. You know, the OS is going to manage those peaks to say, okay, you know, when I receive this one, I'm going to mask the other ones, and so on and so forth. But that's going to be the OS who's going to manage that. So basically, the OS is going to manage the peaks, right? And the peaks have also interrupts and so on. I mean, that's too much detail, but yeah, they are also devices actually. So what happened when the CPU receives an interrupt on the interrupt vector? Okay. By mask, you mean set to 0? No. By mask, I mean like ignore the interrupt. Okay, I don't mean to set it to 0. So here, so when the CPU receives an interrupt, so here it's going to receive a signal on the interrupt vector, and it's going to read this. So it's going to stop everything it does. Okay, so the CPU stop the running programs, transfer to the control to the corresponding handler. So here it's going to stop the program, and then the CPU is going to look at, of course, it's going to read the interrupt number. Okay, and there is a certain number, and then the CPU is configured to have a table, and this table is going to say for each interrupt number which handler to execute. And here the handler is actually going to be an address of the program stored in memory about the piece of the code that is going to handle this interrupt. So here, for example, if you have the system clock kind of doing an interrupt on IRQ0, for example, here it's going to say, okay, for IRQ0, execute the program at the address here, and that's going to be our handle timer interrupt. But this is the thing that we write, as the OS designer, right? So in Pintos, it's already implemented for you actually. So you have this handler and interrupt timer. Here it's going to execute it. So here, what it does usually, it's like the first thing it does is like it saves the current running program, okay? Because you know the CPU is running, the instruction pointer is pointing to something. It has an EIP, the stack. It has registers and so on. So the first thing it's going to do is like, of course, it's going to save the current running program, right? It's going to save all of that. And again, in the video I showed you about Pintos, I show you that, right? There is a piece in the code in Pintos where it does this saving the context. The handler execute the functionality. Okay, so you know behind every interrupt handler, we do something, and then once it's done, we're going to resume. And usually it's like it restores the running program. Okay, it restores the registers, it restores the IP, and so on and so forth, and then resume the execution. Okay. But I mean, meanwhile, we might have changed stuff, right? You will see, like, you know, we might actually change switch thread and so on and so forth, but it doesn't matter, right? At the end, there is the idea of like, you know, we're going to resume, you know, we're going to bring back some state, and we're going to resume the execution. Okay, so where are these interrupt handlers on your OS, if you want to look at it, right? So on Windows, for example, it's they are all in the program called msinfo32.exe, right? But it's a binary, you're not going to see much, right? On Linux, same thing, the binary is inside /proc/interrupt, okay? If you look at the kernel, you're going to find the interrupt.c in the source code. But if you want actually just looking at Pintos, if you look at src threads interrupt.c, you're going to find the interrupt handlers. Okay, so you're going to find exactly what I just told you about. So you're going to find the timer interrupt, you're going to find the interrupt numbers, and so on and so forth. You're going to see also how the interrupt descriptor table is initialized, and so on and so forth. Right? But again, this is implemented for you, right? You don't have to touch that. So an example here, so when you press a key, for example, on your keyboard, here's really what's happening behind the scene, right? And all of that is happening really fast, right? So the keyboard, you press a key on the keyboard. Of course, here the keyboard, what it does, it writes some data into some registers and so on. When everything is ready, it's actually going to ring the CPU. What I mean by ring is actually going to send an interrupt to the CPU. But again, we have seen it's not directly to the CPU; it's going to send it to the PIC, right? The PIC is going to handle it, and here, it's going to decide, okay, can I forward this interrupt basically to the CPU and so on. It depends on the state and stuff like that. And if so, it's going to send it. So it's going to translate this kind of signal into a vector number, and then send it to the CPU. Right? The CPU, as soon as it receives that, stop the running program, and then look at the vector number, look at the corresponding table, and then call execute the handler, right? Execute the handler. What the handler is going to do here in the case of a keyboard, right? A key has been pressed. Is going to talk to the IO device, and it's going to read the data of the key that has been pressed. Okay, we're going to see that a little bit later, a little bit more about input output, but that's basically the idea. And for that, there are special instructions called in and out to actually read the key that was pressed. Then the handler does something, okay, with this key that has been pressed. On Linux, for example, or even on Pintos, it's kind of similar. It's actually going to write that into a file, okay? And because in Linux, everything is a file. I mean, in Unix systems, everything are files. So here it's going to write it in a special file, and then that's it. And then it's going to resume, right? So you see, it's not actually going to run a program or and so on and so forth. It's just going to run the program. Now what's going to happen is like the program that needed this keystroke, when it resumes, is going to see that there is this key that data has been added to this actually input file here. That's going to be the input file. I mean, system in, for example, on Linux, and it's going to read that directly from the file, right? But the handler, the only thing it did was it reads the data from the device and then put it inside the file, and then that's it, restore. And all of that is happening all the time, very fast. Okay. Let's talk about context switching now. So now that we know about the interrupt, let's see how we're going to use this interrupt to actually switch between threads. Okay. So the idea here is like, okay, we have multiple threads. They're all going to run concurrently. But again, the CPU is going to execute one at a time. Okay. So, if you have 10 threads running, only one will be actually running. So here, only one, we have the status running. Again, this is assuming if you're on one core. Of course, if you're on a 4-core CPU, we could have 4 threads running in parallel this time, right? But let's simplify. Actually, it doesn't change the logic. Let's simplify. We have 1 core. Several threads might be ready to execute. So you might have several threads that are actually ready to be executed. So you might have several threads that will have the status ready. Some threads might be waiting for an IO. So for example, here, it's trying to read for something. The IO device is going to take some time, so it's going to be waiting. Waiting in the sense that, it's useless for the CPU to execute it because, it stopped. You are at a phase in the program where you are waiting for some kind of an input and there is nothing else you can do. Okay. So here, waiting, we're going to have a special kind of status here that says, I'm waiting for something. And of course, when you receive the IO response, okay, we're going to talk more about IO later again. But when you receive the IO response, it's going to be an interrupt. You handle the interrupt, And then, you might actually you say, okay, that thread was waiting for that IO. I'm going to change the status, and you put it back to ready. Okay. If I were to summarize in a nutshell, what I just say is the following, right? When you create the thread, so first you create it. You are in the initialization phase where you set up a bunch of things. Okay, you set up a bunch of things. Once it's done, it has been fully initialized. You put it on the ready status. Okay, and the ready status, the OS knows that now it's actually a good candidate to be scheduled. Okay, we'll talk about that later, but basically to be executed by the CPU. Okay, so at some point, if this thread is elected to run, okay, and only one at a time is running, then it's going to be running for a while. It's going to be running for a while until what? Well, until several things happen. Okay, three things. Either actually there's a timeout, okay, of the system clock that says, okay, your time allocated is over. Okay, and if it happens, it's going to stop the program and then put it back on the ready state, and then basically execute another one, right? Another one is going to be elected, and so on and so forth. At some point also, what can happen is like, it didn't reach the end of the timeout, but at some point you do a IO request. Okay, so for example, you write a program that certainly needs something from the IO. I don't know, read something from the USB, read something from the disk, actually, read something from the keyboard or whatever, right? So in that case, the program is stuck, right? It has to wait for the IO. And we will see later that, we are not waiting for the IO. Instead, we can stop the thread. We put it on the status waiting, and then we execute another one. Okay, again, another one of the ready ones will be elected to run, and we run. Okay. At some point, while we are waiting, if there is the IO response, there's going to be an interrupt, and the interrupt handler most likely is going to change the status to waiting to actually now ready, so that it can be actually resumed, right? Also, a third thing that can happen while you're running the thread is like the thread is finishing. Okay, there's nothing else to run. You're done with you reach the end of the program and you stop it. And when you stop it, you terminate. You have to kind of clean stuff on the OS and so on. It can also actually terminate if there is a fault. Okay, so what's a fault? For example, you divide by 0, the program stops. So all the faults I told you, like page fault, we talk about it later. But anything that says erase some kind of an error. You will see later that exceptions. Okay, what we call exceptions is like, in C there is no exception, right? In pure C, but modern language like Python and so on, they have exceptions. Exceptions are actually handled as a default. Okay, they actually generate a system interrupt and so on, right? But there is some kind of handler, a special handler, Python handler, for example, and so on, that takes over. But yet at the end, most likely it's going to terminate the program. Okay. All right. So you see that there are different states here. So maybe here, this is a slide actually to repeat a little bit what I've said, right? So when there is going to be a context switch, when are you going to switch between threads? Well, either the OS receives a fault, okay, a problem, okay, and it's going to probably terminate the thread. It's going to suspend the execution and terminate the thread, or you receive a system clock interrupt, okay, or it does an IO request, okay. That's kind of basically these two branches here, okay. So if it's the case, it's going to suspend the execution, save the context. We talk about that a bit more, and then change the thread state from ready to now waiting, or from running to actually ready or waiting, okay, depending if it's a system clock interrupt or IO request. And then it's going to elect a new thread. It's going to select a new thread, and we talk about that when we talk about scheduling. Change the state to running, and then restore the execution context, and then resume the execution. Right? When OS receives another IO interrupt, it stops the current running program, execute the handler, and then after that resume the execution of the current program. Right? So you see, you can imagine now, in 1 second, you can imagine that your CPU has been interrupted maybe like several hundreds or even maybe 1,000 times, right? This is all going very fast, but it's happening all the time. Okay, that's how just an OS works. Why it looks like magic kind of from the outside is because this stuff are happening so fast, and it looks like kind of very transparent. So you see here, to do all of that, for each thread, we need to keep track of data. We need to keep track of stuff. So first, we need, of course, to keep track of the state. Is it ready? Is it running? Is it waiting? So we need to keep track of that. And we need to keep track of the execution context. What's the execution context? Again, I told you, right, the CPU, to execute instructions, it needs few things. It needs, so it has the EIP, okay, the instruction pointer, the ESP, and it has all, I mean, those are actually registers. And it has all the kind of registers, right? I mean, you have seen that when you did B58, you know, when you have a small CPU, you have actually registers that you can use to do all kind of operations. But there are also other things. I mean, we'll see that later, but it needs also, there are some special registers for the virtual memory, what we call the page table, and so on and so forth. So it needs to keep track of a bunch of things. So for that, we need to actually, you know, if we write an OS, and we do actually, we need to keep track, we need to have some kind of data structures that is going to register of that. Usually we call that a TCB, a thread control block. Okay, so it's a data structure that records thread information. You will have some kind of an ID. Okay, so each thread will have a unique ID. You will have a state, either running, ready, or waiting. Okay, that's actually on Pintos. Registers, okay, EIP, ESP, but also the others. Okay, so it's not only those two. Sometimes the user, okay, actually you don't have that in Pintos. There is no concept of a user in Pintos, but we talk about it a bit later, but on Linux, Windows, and so on, you have a context of user. There's a concept of like, you know, the thread is run by an owner, okay, by a user. And then we need also a pointer to the process control block, okay? Again, this is tied to the process. We're going to see that later, right? But I just put it there because I want it to be kind of complete about the most important things. On Pintos right now, the only thing you have is the first three, right? TID, state, and register. It's very simple. Okay. So also what we need is to have some kind of a queue, right? We need some queues. What queue do we need? Well, at least, you know, we need two, right? One queue for the threads that are in the ready state. Okay, so, you know, and, you know, when it's time to actually elect a new thread, you're going to look at this queue and you're going to choose one thread from that queue. You might need another queue also for the waiting. Okay, so if you're waiting for an IO device, and here maybe you need actually several queues for each type of IO device, right? And so on. Again, that I don't want to you know, I mean, I don't want to overly complicate here, but for project one, for example, at least what you want to have is a queue for the timer, right? And so on. And here the idea is like, you know, when you receive a timeout, you know, you're going to wake up some threads in this queue. Okay. So again, I don't give too much detail about that, but I mean, you're going to see that in the project. All right. I'm going to talk about synchronization. Maybe here, I don't want to start synchronization and then stop. So do you have any questions first about what I just covered? No? Okay. So let's do that. Let's take a nice 10-minute break. And then we come back at 12 o'clock exactly. And then we have 1 hour to basically cover synchronization. It's a big, it's a bigger chapter here. Okay. So we come back at 12 o'clock. Okay. So few interesting questions on the chat. So I'm just going to repeat if you don't watch, I mean, if you watch the video later. So here, some question, is there, for example, what's the TCB in Pintos? Well, Pintos is the thread struct, right? So you can look at it and you can see what's actually in this struct. Is there a register that points to the OS interrupt handler in x86? Actually, what you have, yes, it's like you have the CPU has a special register that is going to point to actually the table, okay? And the table has the mapping between all of the interrupt number and the address of the handler. Yes. When you switch context, where is all registered data for that process stored. They are stored on memory, right? So if you switch context, you're going to read all the registers, and then you're going to store them back in the memory. In memory, I mean, where? Actually, in the so when you create a thread, so the first thing you create is actually you instantiate an instance of the TCB, right? So the TCB actually records the state of the thread. So when you are interrupted, when you save the context, it means you look at which thread is currently executed, and you read all the registers, and then you write them back into that data structures. Okay, and then same thing, like when you resume the execution, you look at you know which one you want to resume, so you go into that data structures, you read all the registers, you put them back onto the registers, and then you resume the execution. Okay, so same thing. All right, so let's talk about synchronization. So now what we have achieved is that okay, so we have multiple threads going in parallel, but again, as you will see, so now they can actually read and write the same address in memory. Okay, so say differently, for example, they can have the same variable, and then they can both you can have two threads that are actually going to modify the same variable. Okay, but what you can have also is like you have two threads actually going to interact with the same IO device. You can have two threads that read the same file, for example, and so on and so forth. Right? So threads are going to interfere with each other in a way. So there is a need for actually synchronizing some operations. Otherwise, bad stuff can happen. Okay, and we're going to see that now. Here, well, let's take a very, very simple example here. Okay, so imagine I have kind of two threads, ping and pong here. And those two threads are doing something very, very simple in C. For example, one is printing ping, the other one is printing pong. Okay. So here, again, this is in C, right? These are not kind of instructions on the I mean, these are not really instructions in assembly, right? But this is going to be compiled into instruction in assembly. So here, imagine you have these two programs and you run them. What's going to happen? Okay. What you would like maybe to happen is the following, right? You have one line of ping, one line of pong, one line of ping, one line of pong. Okay. But what's going to happen? Well, anything can happen, actually. You can have ping, 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 pong, pong, ping, pong, right? But you can also have like PI and then, PO again, right? You can have P and then, several Ps and then not so, I mean, you can have P and then pong, right? So here, if they are not synchronized, both of them are going to try actually to write every character one at a time on the screen, for example. Okay, and so this program can actually interfere, right? If you don't actually synchronize the access to the screen. Okay, so this is kind of a problem here. So we can have like chaos. Another example here. This is more like an abstract example. It's very like just to understand the concept. It's a very classical example that you find in the books. But so the idea is the following, right? Imagine you have two people living together, Alice and Bob. Alice comes back home and then look at the fridge and out of milk. So she decides, okay, she's going to leave to the store. She arrives at the store. She buys some milk. Come back, put the milk in the fridge, right? But imagine meanwhile, for example, she's at the store and Bob also comes back home and he opens the fridge and say, oh, there is no milk. So again, he's going to go, actually, he's leaving to the store also. Imagine somehow they don't run into each other, right? They don't run into each other, so they cannot, both of them are going to buy milk, and then he comes back and he arrives at home and too bad, they have too much milk, and no, they are not going to consume that much milk, and it's fresh milk, so it's going to go bad. Okay, so you see here, bad stuff can happen when you don't synchronize properly, right? It's true with humans. It's actually true with threads as well on the OS, right? Yeah, they should have called each other. Maybe that example was actually designed when we didn't have cell phones. Okay. Okay. But I mean, yeah, the phone or even a Post-it note and so on, that's synchronization, right? But let me take okay, so the milk one is kind of abstract. Let me take a real example, okay? So here, I'm going to take an example of two threads. Okay, it's not going to be ping pong. It's going to be even simpler than that. Imagine here, these two threads shares a variable x, right? And they share it because it's completely possible, right? They, the variable is going to be stored somewhere in memory, and they just like, read the value at the same memory address, and then they're going to do something with it. Thread one is going to increment it, okay, plus plus, and thread two is going to decrement it, right? So if you run those programs, in parallel, what's going to happen? Imagine here we initialize the x to 0 at first, okay? You can argue the following, right? Here, it doesn't matter, right? It doesn't matter the execution because, one is going to do +1 and the other one -1. So it doesn't matter who goes first. At the end, the value, once these two programs have completed, these two threads have executed, the value is going to be 0 still. Okay, you can say that naively. Well, not really. Okay, no, actually, something bad can happen. For that, we need to actually look at the instruction level because, again, this plus here in C, it's not atomic. What I mean by atomic, when you're going to compile the code, this is going to translate into binary instructions. And those binary instructions are usually, it's done in 3 instructions, okay? I mean, there are ways there are now more advanced instructions and so on, but here I'm gonna, just to explain the problem, I'm gonna compile it into 3 instructions. One is going to be load, okay? You read the value x from the memory, you increment it, and then you store it back, right? Very classic. Of course, thread 2 is going to do kind of the same thing, but it's going to decrement it, okay? Only this one is going to change. Okay, so if they are not atomic, and those 2 threads are run concurrently, with context switch and so on, what can happen? The problem here is like the following, right? This thread might run, for example, imagine thread 1 goes first. At some point, it is going to receive an interrupt. Imagine it's a timing interrupt, right? And somehow the interrupt occurs here, right? It's not going to happen in the middle of an instruction, no. But it might happen, after, for example, the load, right? Or after the increment. And then, we're going to switch context, and we're going to switch to thread 2, and thread 2 is going to execute. So what are the things that can happen? Now, imagine several scenarios, right? Imagine scenario number 1 here, when you load, you increment, you store, and there is a context switch, or maybe like here, the program is actually done and so on, and then you execute thread 2, load, decrement, and store. In that case, it's going to be equal to 0, right? Okay, and here you might argue, this is fine. This is what I meant to do when I write my C code, right? But there's another scenario here. Look at this one. We load x, and when we load x here, x is value 0. So we load it. But then there's context switch. And then now we load actually, we go to thread 2. Okay, I hope you can see colors here because I use colors. So here, this is thread 2, and thread 2 is also going to read x. X is still 0 in memory, right? Thread 1 is going to increment, thread 2 is going to decrement. Okay, so 0 is going to be 1 is going to be 1, and the other one is going to be -1. But then, one stores x, and then the other one stores x as well. So here, x is going to be equal to, well, the last one that actually pushed the value to memory, right? So here, it's actually going to be -1 because it's thread 2 who has pushes last, right? It's kind of like, 2 people writing on the file, and it's the last one that writes to the file that has the final result, right? Kind of. So here, but you can have another scenario, right? I mean, it's kind of the same thing reversed, but now it's going to be equal to 1. And here, so at the end of the day, you have multiple scenarios, okay? And again, this is not deterministic. You're going to run it once. You run it 1 time, 2 times, 3 times, 10 times, 100 times. The sequence of execution might be different every time. That's important, right? It might be different every time. Why? Because there are other threads running on your computer. Of course, if you have only these 2 threads, and a very simple system, most likely you're going to replicate that. But on a complex system where you have other threads running and so on all the time, this is impossible to predict that it's going to have the same kind of execution. Right? In the end, you have many possible scenarios, and the outcome is going to be that x is going to be either 0, -1, or 1. Okay, but you cannot predict it. And you can run it like 10 times, maybe you're going to have 0, but then the 11th time is going to be -1. Okay, that's what's hard. This is the kind of bug. Here it's important, right? This is what we call a race condition. And in computer science, I mean, for us programmers, this is the hardest thing to catch. Because a race condition, so it's a bug, but it's a bug that we're not used to that kind of bug. It's not a bug like, there's nothing bad that happened in a sense that, there's no error. There's not like, the program doesn't stop and tell us, oh, there's something wrong, right? We are used to this kind of bug. Here, no, the program executes and it's just like, it's going to be a weird result. And it's even worse because it's going to be a weird result sometimes. Okay, it's not a bug that you can reproduce all the time, right? I mean, in AO8 and so on, you're used to the bug that, you run it 10 times. If it's 10 times the same problem, you're going to have 10 times the same bug, right? But here, it's a nasty thing. And maybe actually you're gonna test it 1,000 times, and you test it, you don't see anything wrong, but then you put it in production, and that's happened for quite often, and then suddenly the bug occurs, right? So you see here, this is for us, I mean, programmers, this is the hardest thing. So we call that a race condition. And again, the race condition might not manifest itself as a bug, right? It's just, at some point there's going to be something, the data is not going to be consistent. Okay, it's always a problem with data. So it's hard to catch, okay? And that's why it's, when you're a programmer, those race conditions and synchronization is maybe one of the harder things that you're going to debug. And that's why that's why C69, you're going to do that all the time because you write at the very low level of the OS. And this is why it's a hard course. So here, the idea is the following, right? What we want to have is to have some kind of mutual exclusion. What do I mean by mutual exclusion is that, when you execute a program here, you would like to, in a way to have that atomic, or at least, it's okay to be interrupted. It's okay to be interrupted. But what you don't want is that another program actually modifies X while you're in the middle of actually modifying X. So here, what we're going to call is like this here, this just, maybe actually this instruction here, we're going to call it a critical section. Okay, a critical section means, while I'm doing that, it's critical. I'm modifying a variable, a shared variable. I don't want to be, it's not that I don't want to be interrupted. You can be interrupted, but I don't want anybody else to actually modify the value until I'm done, right? So here, you see, if you want mutual exclusion, you will need to identify in the code where is this critical section. And once you have identified the critical section, you are going to use some synchronization tools, and we're going to look at these tools to actually ensure this mutual exclusion. Okay, so that you don't have two threads in the critical section at the same time. Okay, only one thread at a time can be executed in the critical section. All the other threads are forced to wait to enter the critical section. Okay, that's what we're going to do. And of course, when a thread leaves the critical section, another one can enter, right? So let me talk about the it's kind of like the same example as with the X, right? Incrementing the X, but it's a very classical example that you find in textbooks. It's called the producer consumer, right? So here, imagine the following. You have a buffer and you have two programs running concurrently. One is producing, meaning one is actually writing into the buffer. And the other one here, the consumer, is actually reading from the buffer. Okay, so we have two programs, two instances, so two threads running in parallel. Let's see. Does this assume that both threads are instances of the same program? You mean for the critical section? Not necessarily. Okay. No, here, for example, no, I have two different programs, and so I'm going to have two threads instantiating different programs. No, so not necessarily. Okay. But you can. You of course. I'm going to show you an example towards the end. We're going to have one program where actually it's where you have multiple threads instantiating the same program. Okay. So here, if you have that, okay, so a buffer has a fixed size, okay, we don't want to have an infinite buffer. So basically the algorithm can be like this, right? So first you're going to produce an item, whatever that is, right? I don't know, you're going to generate a random number, you're going to calculate something, it doesn't matter, right? So you generate an item, and then you're going to push this item into the buffer. But first, you're going to wait that the buffer is not full, right? If it's full, you're going to wait, and wait means you're going to have a while loop. Okay, let's make things simple. So you wait, and then when the buffer is not full, you're going to write. Okay, you write into your item into the buffer. Okay. Consumer, same thing, right? It's going to wait that there is something in the buffer. Okay, we're not going to read an empty buffer. And then when there is something in the buffer, we're going to read that the buffer and then consume the item, whatever that means, right? You know, we read the value and something we do something with it. Okay, it doesn't matter. So here, what is the critical section? Well, the critical section is kind of here, right? It's like our X. We have a shared variable, which is our buffer, and we don't want to have two threads, you know, messing up using that variable at the same time, because we're going to have some side effects. We're going to have this kind of, you know, the same thing as before. So we want each program to kind of access the buffer separately. We want to have mutual exclusion on that. So here we, you know, as a programmer, we identify that, okay, our critical section is actually these two C instructions here, while and write, and we want to synchronize that. And we want to have only one thread at a time doing that. Right? So here, for example, I want to do that. I want to write into the buffer, and then here, when I exit the critical section, another one can be another producer, by the way. Okay, but here, let's simplify. Here, we have only one producer, one consumer, but we have another consumer actually that can consume, read the buffer. Okay. Okay. I see some questions here about Pintos. I don't want to digress on Pintos. Okay. Sorry. But we talk about Pintos a bit later. Let's focus on that right now. Okay. So here, the requirements. So to ensure mutual exclusion, what we want is like one thread at a time in the critical section. Okay, and that's something we want to ensure. We call that the safety property. Okay, nothing bad can happen because we're going to have only one thread at a time in our mutual exclusion. Okay, again, assuming that, you know, we have, as a programmer, we have done our job correctly, right? We want also progress. Progress means that at some point, if a thread is not in the critical section, eventually it's going to enter in the critical section. Okay, because a thread that was currently in a critical section eventually is going to leave, right? I mean, we want to avoid having, you know, a thread always holding the critical section. If possible, we want that to have a bounded waiting, meaning no starvation. Okay, so if you have multiple threads that compete, all of them to enter in the critical section, eventually all of them will be kind of will be able to enter, right? We call that the liveness property. Okay, it's important the stuff. We have safety property, progress property, liveness property. Okay, and of course we want to have performance. Okay, the overhead of entering the critical section and exiting the critical section, because we're going to need to do some stuff. Okay, we're going to need to synchronize. Should be you know, should be relatively low compared to what we do, right? I mean, if you're just like incrementing a variable and, you know, it takes tons of instructions to just enter a critical section, it's not very performant, right? So that's what we want. But in the critical section, make sure there is no switching. We'll talk about that. Here, we can either make sure that there is no switching, or switching is fine, okay? And it's actually better, the second one. Actually, switching is fine, but you don't want to switch to a thread that is going to enter in the critical section as well. You don't want another thread to actually execute something, for example, is going to mess up with our buffer. Okay, so here actually the best way to implement that. Okay, I'm going to talk about it in the next half an hour, right? But just to answer your question, is not actually to prevent context switching. We're going to have, it's better actually to leave context switching, but we're going to make sure that no other thread enters the critical section. And maybe here, let me give you actually an intuition, right? Imagine if you were able to prevent context switching, it would be really bad. Imagine here that, you know, every time you have a program running on your computer that needs to access a shared variable, you know, disable the context switch, or the other program would be frozen. Okay, that would be bad, right? I mean, no other thread could run, right? That would be bad because everything would be frozen, right? I mean, I couldn't use a microphone and so on and so forth. So you don't want to avoid context switching. Okay, I will talk about that in a few minutes. So for that, first we need some synchronization tools. I'm going to talk about 3 of them. Okay, 2 are the most important. So if you read the textbooks and so on, they start with there's different ways to approach it. Here, I'm going to approach it with first, I'm going to choose the concept of lock. Okay, why? Because the lock is kind of simpler, I believe. Okay, so the lock here, we call it also a mutex. Mutex, why? Because it's a mutex for like mutual exclusion. It's going to be some kind of a programming construct that will allow us to actually synchronize. Okay, so here a lock, it's very simple. It supports 3 operations: init, acquire, release. Okay, it takes no arguments. Okay, you initialize a lock. Okay, you have a lock. Now you can have a variable lock, and then you can acquire a lock on this variable and then release. The idea here is like the lock is going to be a shared variable. Okay, of course you're going to share the lock with another thread, but if one thread actually acquires the lock, the other thread cannot, and it's going to be blocked, right? And it's only when the one thread is going to release that lock that the other thread is going to be able to acquire that lock. Okay, let me show you more better on the producer consumer here. And this is a bad example. Okay, I'm going to ask you why. But here, imagine the following, right? So here I'm gonna, I produce an item. Okay, that I do it. I don't need. This is not in my critical section again, right? But here I acquire the lock. I write my thing into the buffer, and then I release the lock. Okay. So if I do that, another program here, the consumer, another thread, will be blocked. It will not be able to acquire the lock. So here you will have only one item at a time that we enter in this critical section here. Okay, my critical section is kind of like 2 instructions across these 2 programs. Okay, and so on until you release the lock. Okay, so you see here, just to show you, actually why I say it's bad. Well, because I kind of got rid of the loops, right? So the producer might write into a full buffer, the consumer might read into an empty buffer. I kind of got rid of those parts, but this is just to show you, right? If I bring it back, it's going to work like this. But maybe here, okay, let's be naive here. If I want to bring it back, I could do the following, right? Again, when I'm going to check if the buffer is empty, I'm kind of reading the buffer. So I know this has to be in my critical section. Something bad that you can do is the following, right? You acquire the lock, and then you have your infinite loop here that says, is it full? If it's full, then I'm going to wait. But you see here, if you do that, there's a problem, right? Why? Because you have acquired the lock, and you're just waiting on an infinite loop. And you're waiting on an infinite loop. You are basically waiting for somebody to actually produce something. But wait a second, nobody can produce, because to produce, they need also to acquire the lock. Okay, so that's why if I just put like naively, if I put back my loop here, it's not going to work. So you can tell me, okay, I can put it outside. But wait, if you put it outside, then well, that's a problem, because now you might read the buffer when the buffer is actually being modified here. Okay, so that's bad. So here actually the real, the good solution here is the following, right? It's actually do that. So before testing if the buffer is full, of course you need to acquire the lock. Okay, the lock is going to make sure that nobody else is actually messing up with the buffer when you read it, because for that, of course, you need to read the buffer, right? So you read it. If it's full, if the buffer is full, okay, you cannot write, but you need also to release the lock. So right away here, we're going to release the lock. Okay, something here. So this one you might not find it in the books and so on, but on the OS actually, what you would do is like yield. Yield means there's nothing I can do. Okay, it's not going to be useful here that I go in an infinite loop to actually reacquire the lock, retest it, and so on. So I'm just going to yield, and then next time I'm going to be scheduled, I'm going to acquire again the lock, and then I'm going to check again the buffer. And if it's again full, I'm going to release the lock, yield, and so on and so forth. Okay. Finally, at some point, this is not going to be full. So here it means that condition will be false. When I arrive here, I have acquired the lock necessarily, right? Either it was here and the condition was false, or I was in the loop and that I acquired the lock and the condition was false. Okay. So yield. Question from Arena here. Could you explain yield again? Yield is a way to actually tell the OS. It's like, oh, I mean, you can remove yield, by the way. If you remove yield, it's fine. It's going to work. But here it's something to say, okay, no, there's nothing I can do. I yield my CPU time. And so here, yield is a special function that you call in the OS to say, oh, you can switch to another thread. I don't need the CPU. Okay. Look at Pintos. Pintos, you do a lot of yield, right? Especially with timers and so on. When it's the timeout has not when the timer has not timed out, you actually yield, right? So look at Pintos. It's the same kind of idea. So here you write into buffer, and of course you release the lock, right? On the other side, it's kind of the same program. You acquire the lock while it's empty. Okay, if there is nothing to read, you're going to kind of release the lock, yield, say, okay, somebody else can execute, and somebody else actually now can actually acquire the lock and so on, because of course you have released the lock before yielding, right? And then so on and so forth, right? So and here, of course, once there's something in the buffer, you read the thing from the buffer, you can release the lock right away and then consume your thing. Okay, so that's a good producer using a lock. This is not the only construct. So there is another construct called a condition variable. Okay, so condition variable here, and by the way, you have that implemented in Pintos, right? Lock is implemented in Pintos. A condition variable is also implemented in Pintos. What's a condition variable is basically you can unlock the lock and sleep if a condition is while a condition is false, right, or true actually, and before resuming execution. Let me show you an example, right? So you have wait, you have signal, and you have broadcast. So here is how it works, right? So here. I forgot something about, okay, I forgot the mutex here. But first you acquire a mutex, because here you're going to check, so here you have a lock, okay, you acquire the lock. While you are doing that, then here you do a condition wait on the buffer being not full, right? And while the buffer is not full, you pass a condition that actually takes a lock, and it's going to actually take the lock only when this condition is not satisfied. Okay, so you do that, and then it's kind of the same thing. It's actually syntactic sugar in a way, right? It's syntactic sugar, and then once this condition is true, okay, you go out of the loop. You're holding the mutex, and then you can do your things. When you're done, you can actually signal it, and you signal actually here not empty, right? And so on. So that's a way to use a condition variable. I don't know. To me, I mean, well, let's talk about that later. Any questions here? What does the line count wait not full do again? Okay. So here, condition wait. It's basically, I mean, when I say syntactic sugar, you can look at it. It's going to do this in a nutshell, right? In one instruction. Meaning, what it's going to do is like, if it's not full, it's not gonna try to even hold the mutex, right? It's like when this is going to be satisfied, when it's not full, then it's going to actually hold the mutex, right? So here basically we're gonna we're going to loop on that until actually the buffer is not full. Do we need the while loop here? Do we need the while loop? Yes, because no, maybe not. Okay, I need to see how this is implemented actually in Pintos, for example. No, maybe you don't need the while loop. Okay, okay. Let me check that, and then I will post something on Piazza. Okay, I will check that on Piazza. I will answer all of your questions. I need to check also myself. I got confused while I was explaining it. Okay, so let me check that, and then we'll talk. We'll see that. Actually, let's look at it right away. On let's look at Pintos. We can look at Pintos. So Pintos, all this stuff, let me show you right away. It's inside threads. There's something called sync.c. And in sync.c, where you will see it's like, there's all kind of things. So I will explain that later. There are semaphores, but basically here you have the locks. So you see here, lock init, lock acquire, lock try acquire. Okay, that's kind of syntax issue, and lock release, right? So here, here's the condition variable, right? So condition variable actually here, there is a list of waiters. I mean, that's kind of a data structure, right? This is actually to ensure fairness. So what it does is the following, right? So when you do, let's look at, well, const wait. That's exactly what we wanted to see, right? So here, const wait is going to do the following. It's based on semaphores. That's okay. We don't need that. To explain. So here, what it's going to do is the following, right? So it's going to actually push itself to a list and then release the lock, that's okay, and then acquire the lock here. So here, it's going to put itself on a list, and then it's going to wait. So it's going to wait, right? So you might be right in the sense that here, I don't need the while loop, okay? So I'm going to try to implement that and modify my slides. So here, it's going to put itself on the list and then wait. Once the condition here, which is the condition here that we have passed as argument, becomes true, which is, for example, it's not full, okay, then one person that was waiting there is going to be wake up, and when it wake up, it actually takes the sema down here, which actually it holds the lock, okay, and it acquires the lock. So yes, you don't need the while loop, I believe, okay, and signal, what it's going to do is like, it's just actually going to release the lock, okay. So here, let me correct right away. Yeah, I think my slides need to be modified. You don't need the while. Okay. Yeah, you don't need to recheck the condition because the thread has been already locked. Yeah, correct. Okay, so I can modify that later. All right. Yeah, while can be replaced with if, yes. Yeah. Okay. So here, another synchronization construct. So here's the thing. So when I learned about synchronization, I learned about semaphores. Okay, I mean, I've learned about locks and so on. But to me, the semaphore is the most versatile programming construct here. Okay, and so this here, you will see it's a little bit different on the lock, but the idea here is like, I'm going to explain that later, but you can implement, once you implement a lock, you can implement semaphores on top of the lock, okay? And of course, the condition variables works on top of a lock. But something you can do also is like, once you have a semaphore, you can actually implement a lock on top of semaphores. And that's actually what Pintos has chosen to do. Linux is different. Linux, they implement lock and then implement semaphores on top of lock. But Pintos has decided to actually implement semaphores and then do it on top of lock. To me, I believe as a programmer, once you know about semaphores is versatile enough that you only need semaphores. You don't need even to lock and condition variables. Okay, that's why actually I've never used condition variables. I always use semaphores myself. So how does it work? First of all, it's something old. It's like 1968. Semaphores, you can think about it as an integer, and you're gonna have two operations on this integer: increment and decrement. Okay. Originally, it's called P and V, right? Because it's in Dutch. I don't know well exactly the word, but because Dijkstra was Dutch. Okay, so you have P and V to increment and decrement. So here, when you're gonna let's start with increment. That's simpler. Okay, so when you do you do V or you do up, okay, semaphore up, you're gonna increment that integer. Okay. When you do P though, when you decrement, you're going to decrement that integer. But this integer can never be zero. Sorry, it cannot never be negative. It has always to be greater or equal to zero. So what happens when it's already zero and you try to decrement? Well, this is where you're going to be blocked. Okay, so a process is going to be blocked if you try to decrement a semaphore that is zero. Okay, so for that, we need to wait for somebody else to actually do a V on the semaphores to increment it, and then finally being unblocked, and then continue, resume the execution. Okay, so here, so the idea of the blocking mechanism is like with each semaphore, there is a queue of waiting thread. Okay, a little bit like what we saw in the condition variables in Pintos. Okay, when P is called by a thread, okay, if the semaphore is open, okay, meaning no, the semaphore is greater than 0, okay, then fine, we increment and then we continue. Okay, sorry, we decrement and we continue. If the semaphore is what we say closed, okay, it's 0, it's going to be on blocked. Okay, when you do V, same thing. You know, if there was somebody waiting, I mean, you increment, and if there was somebody waiting in the queue, you're going to wake up that other thread. Okay, so and this is kind of done automatically. That's why I find it kind of neat to use two semaphores. So imagine the following, right? And here I'm going to have just a bad producer consumer, again, just to show you the mechanics here. But something you can do is the following, right? You can do, okay, let's do the following. I'm going to have not full here, and I'm going to initialize this integer to n. N is the size of the buffer. You will see why. And then I'm going to have another one called not empty, and I'm going to have it 0. And in a way, you know, it's kind of no, not full and not empty. They're gonna act as you will see how they will be correlated. So I'm going to start like this. You know, this is n and this is 0, right? So here, when you produce, what you do is the following: you're going to wait. That is not. You're going to try to do wait. Okay, same wait or kind of decrement. Sorry, you're going to try to decrement on not full. Okay, and here, so if it's not full, you kind of decrement, and then you write into your buffer, and then you're going to signal empty, right? So you see here how they communicate. You know, one is going to go low, the other one is going to signal is going to go up, right? And at some point, if you produce, you know, you might produce, but at some point it becomes full, meaning this one is going to reach 0, and you're going to be blocked here. You're not going to be able to produce. Okay, somebody else on the other side, on the consumer, has to kind of is going to wait that it's not empty. Okay, so you know, at first when it's 0, it cannot, but then as soon as there is something, because here it will have incremented the variable. Okay, here it can actually go. They read, and here they're going to signal. Okay, so you see here a little bit how it works and why it could be useful. Although here I have a big problem. That's why I say it's bad. It's not working, and it's working in the sense that we are, you know, a producer will not write into a full buffer. A consumer is not read from an empty buffer, but we didn't ensure the critical section. Why? Because here you can have actually a producer writing at the same time as as another one is reading. Okay, so here that's why it's kind of bad, right? I mean, I have not actually ensured the critical section. But it's kind of interesting here, the way I've used my semaphores is like, you know, at least I have ensured that, you know, nobody can read on a full buffer. Okay. Sorry, that the producer cannot write on a full buffer and vice versa. So here, what would be the good way to do that? We need to add one more semaphore. Okay. And here actually, you can call that a lock. Okay. A semaphore that is as value 1 is a lock. Okay, you will see here. The idea is the following. So why it's not full, what you do is like you take the mutex, and then you're gonna try to kind of decrement the semaphore not full. As you do that, now you write, and then when you're done, you signal not empty, and then you signal mutex. So you see here, this is kind of working, right? Because on the other side, you know, here you know, by adding this mutex here, we are sure that nobody is going to write into the critical section, right? I mean, while you read, you cannot have a producer because the producer here it cannot reach that mutex, right? Now, does this work? Do you see a problem? I'm going to stop here because it's not simple. But do you see any problem? Can you when I talk about the problem, can you see a execution scenario in which we have a problem? And here the problem is going to be progress. What I mean by progress is going to be something is going to be blocked. You don't see? And that's why actually it's still bad. It's still a bad implementation. Okay, so people say you don't understand the code. Okay, so what is it that you don't understand? This is important here. I mean, this stuff are hard. So
why do we have to use the two semaphores for the consumer producer?
so why I'm using not full, not empty?
Yeah, I'm asking about the not full, not empty, and the mutex. What are all of this?
Okay, so here, if I don't, okay, so let me go back here. So the idea here is like, I'm going to use these semaphores actually to, I'm going to use it. So of course, what I could have done, I mean, at the end of the day, what maybe here, if you want to avoid having to do that, you can basically go back to that, right? So let me tell you here, I can actually re-implement that, and I can just replace the lock by a semaphore of value 1. Okay, so I can do that. If I replace the lock here by a semaphore of value 1, I do exactly the same thing. But here, just to show you how semaphores can be powerful. Again, I believe, as a programmer, that's why I prefer to teach semaphores, because if you understand semaphore, it's versatile enough that in some situations, it's going to be the code is going to be more elegant, it's going to be more simpler, and so on. But you need to understand a bit what's going on. So here, what I've done is like I've used the semaphores to actually keep track whether a buffer is full or empty, right? So here, so the way I use it is the following, right? So I have one semaphore called not full, and not full is going to have n. N is basically, the number of slots left in my buffer. So here, when I start here, if I have a buffer of size 10, the semaphore is going to be 10. Okay, so I'm going to say I have 10 rooms in my buffer. So here you can see I can produce, because every time when I do same weight, again, remember, same weight, decrement. So I'm going to decrement that variable. Okay, so of course, because every time I actually produce, I'm going to reduce the buffer, right? If nobody reads, I start with 10, I produce 1, so now it's 9, now it's 8, now it's, and so on and so forth. So here I use a semaphore for that. The good thing here, using semaphore, is like, I don't need a while loop or whatever. I'm automatically going to be blocked if this value is 0. Meaning, if I've produced too much, at some point, I'm going to be blocked. Okay? Yes, wait, decrement, signal, increment. Okay? No, yeah, it's wait, decrement, signal, increment. Okay? So here, as we do that, we can do the same thing actually to actually see if something is not empty, right? Because here, we're not going to wait on not full, right? I mean, it makes no sense to actually wait for it to be not full to actually read on the buffer. Okay. So here the idea is like we're going to have another semaphore which is not empty, and here it's kind of like the number of spots that have been taken. Okay, that have been read. So of course here, this plus this is always going to be equal to n at the end, right? That's why we start with n0. So here, what's going to happen is the following, right? Once you have written, you're going to signal not empty, incrementing the semaphore here to 1, right? And you increment to 1. So here, So here you increment to 1. So you have incremented to 1. So here this one can go, right? And this one is going to read until actually is going to be blocked, and at some point when it's going to be when not empty is going to reach 0 again, right? So here we are using those two semaphores here as a good mechanism to keep track of a buffer. What's good is the following also, because In semaphores, remember, right? When you're blocked, you are put kind of to sleep. And you're going to be wake up only when it's there. This is actually more efficient because here there is no while loop. You're not fighting for a lock, right? Here, basically, the good thing is like, when it's going to be your turn, when you're going to be, it's going to be either not empty or not full, you're going to be waken up and you're going to be able to resume execution. This is a very efficient way actually to manage this kind of stuff. But now here, what's the problem? Okay, I have achieved the job of actually, not wait for I'm not waiting for the buffer to be full or and so on. I mean, I'm not waiting. I'm not busy waiting. Okay. Here, automatically, when the buffer is not going to be full, I'm going to be awakened. When the buffer is not going to be, when there's going to be something on the buffer, the consumer will be awakened if it's there. Okay. But there is something I haven't done well, which is still I can have somebody writing at the same time as reading. So kind of like, I put all of that and I forgot to do the most important thing, which is synchronize the access to the buffer. Okay, at least for writing and reading, right? So I haven't done that. So here, well, how can I manage that? So here, I will still have a mutex here. So maybe if you want, I could have put it maybe closer to the right. I mean, it's kind of the same, right? But here, I put the mutex here, and I'm going to ensure that when I write, nobody else is producing or consuming. I'm going to be the only one touching the buffer. Okay, so that's why I put the mutex here. Again, I still have my semaphores to kind of manage, when I can write into the buffer or read into the buffer. But then when I manipulate the buffer, I have this mutex here to ensure it. Now, is that more clear now?
I'm still confused about the same signal, not full. What is it doing?
This is actually here. So imagine the following. Not full is going to increment the variable, the semaphore here, not full, right? Because of course, imagine the following, right? Imagine here, the producer produce a lot of them, and at some point it becomes full, right? It becomes full. Let me actually, so the question you're asking may be better on that, right? So here, this producer is going to be blocked when that reaches 0. And that will reach 0 when actually, he has written n items in the buffer. Okay? So basically when the buffer is full, right? So, but here a consumer, when it's going to consume one item on the buffer, okay, after consuming one item of buffer, the buffer is not full because you have consumed one item. So of course it's not full. So here you're going to increment the variable not full to actually signal, okay, to signal that somebody else can go there. And who is this somebody else? Well, a producer who was waiting actually to produce, right? Because for sure he can go on. For sure, now it fits value 1. For sure now there is at least a slot empty and he can produce. Okay.
So not full is when you have a minimum of one free slot.
Yeah.
For the producer.
Yeah, correct. Yeah, and not empty is kind of the opposite, the reverse.
Got it.
So here we still have a problem, and this problem is a big problem, which is called a deadlock. So what is a deadlock? It's actually really bad. Imagine the following here. Imagine this sequence of execution. Imagine a producer produce, okay? So he produced like n objects, okay? And so here at some point it's going to hold the mutex, but then it's going to be stuck here because the buffer is not full. The buffer is full, right? So if the buffer is full, it's going to be blocked here. If it's blocked here, what's going to happen? Well, here, not full is going to be, the producer is going to be unblocked only when the not full is going to be signaled here. But this one here can never be signaled. Why? Because you need to actually reach that line, you need first to have the mutex. And to have the mutex, well, you cannot have it because, well, the producer is holding it and the producer is now stuck. we call that a deadlock. Okay, and that's the worst bug that can occur. By the way, when a deadlock occurs on an OS, it's really bad. This is a blue screen of death in Windows or on Mac and so on. It's like when everything freezes, potentially there was some kind of a deadlock, okay, somewhere. Not always, but it's a classic kind of thing. So here, there's a problem, right? There's this problem of things. So what's a deadlock exactly? It's like when you cannot make progress. Okay, so that's actually a grid deadlock. Okay, with cars. Okay, you can see here nobody can progress, right? I mean, this is they're going to be stuck forever here. But that's the idea. Usually it happens when you have this kind of scenario, right? So again, I'm not giving you here. I'm giving you an example. This is a classical example. It's not the only example of deadlock, right? But it's kind of a classical example here. You have basically two semaphores or even two locks, right? I mean, two semaphores. You know, you take the first one, and then the other one takes the second one. Okay, and then both of them need the semaphore that the other one is holding. And if both of them needs that, both of them are stuck, and they will never. Well, this is the end, right? I mean, you can just turn off the computer here. Okay. So that's usually what we call deadlock. Here, there is this kind of deadlock here because it's going to wait for not full. Not full is going to be signaled here, but to signal this one, it needs mutex, and mutex is held actually by the producer. So here we have another example of deadlock, right? So you see here we have usually a deadlock when you have two threads with this kind of like inverted semaphores. Right now, first it gets SEM1 and SEM2. And then the other one gets SEM2 and SEM1. That's a classical kind of deadlock. But here I have another deadlock where actually both of them kind of take the mutex at first, but there is a deadlock as well. Okay. So that's bad. How do you fix that? Well, let me show you the good actually solution. The solution here is actually just to invert, and then suddenly it works. So you see here, I mean, this is why synchronization is really hard. I mean, you see, you can be very confused and not see what's happening in just three lines of code. So here, by just inverting that, now it works. Now it works. Why? Because here, not full, while you're waiting for not full, you don't hold the mutex. And if you don't hold the mutex, then here, somebody can actually take the mutex and eventually signal not full to you, right? And then you can progress. And here, by doing that, you're ensuring that one at a time actually write into the buffer, right? And this time it works. This time it works. It's elegant. There is no while loop. As soon as it's full or empty, you're going to be blocked on a queue. You'll be the only one actually accessing the buffer, and so on and so forth. Okay. So here, this is a very kind of elegant solution. Okay. How to avoid deadlock? This is hard. Okay, again, read chapter 2 a little bit to talk about that. Usually it's hard, and that's why that's why it takes some experience as a programmer to kind of do this kind of synchronization things. Well, I mean, you are in luck because you are taking C69, and you're going to have synchronization from today until the project 4 in Pintos until you are done, right? There's going to be synchronization everywhere. Why? Because they are shared variables. And they are shared variables, and there's context switch, and we need to ensure that this is properly synchronized. And that's going to be the hard part. Okay, I can tell you, this is going to be the hard part. And you're going to have real bugs about that. Okay. Let's see. It's 12:55. I'm going to cover that, the implementation, and then I'm going to stop. So as I told you, there are two ways to implement those order synchronization. Usually on the system, you want at least to have semaphores and locks. And you can actually implement locks first, and then semaphores on top of the locks. Okay, and that's actually what Linux is doing. First, they implement something we call a spin lock. Okay, it's a non-blocking lock, and then on top of that, they have a mutex, okay, which is actually a blocking lock. Okay, that here I use the term that they use on Linux, right? Spin lock and mutex. And then they implement semaphores on top of that. But on Pintos is different. They implement first semaphores, and then they build the lock on top of semaphores. That's why here, let me show you. Here, you see, the first thing they implement is semaphores, okay? How they implement semaphores, we're going to talk about it right now. But when you look at the lock is implemented using semaphores. Okay, so here you see they do sema init inside. So it's kind of like syntactic sugar on top of sema init. And of course, the condition variables I told you about is actually implemented on top of locks. Okay, so here, let's see. How do you implement? So how do you implement a lock, right? So again, let's go back to the first one. Even if we talk about locks or semaphores and so on, right? What is it at the end? At the end, it's going to be a variable that is going to be either 0 or 1 or n, right? But here, let's take an example of a lock. So here, you know, when you initialize it, for example, you can say, okay, a lock that is actually unlock is going to be 0, and while is 0, okay? So while this is not while this condition is false, you loop, okay? And you loop, and at some point, if it's not, I forgot one thing here. It's like why it's not, why it's yeah, 0 is false. Yeah, no, it's fine. Why this is 0. So if it's false, then okay, now you can acquire the lock. But if it was 1, you'll be stuck in this loop. Okay, and that's how you're gonna wait. Okay, and wait here, it's a busy wait. Okay, you're going to be stuck on an infinite. Infinite. You're going to stop on a loop. Release here, what it does, it takes the variable and then decrement it to 0. Okay. But again, does this work? No, because you can have a context switch, and again, this lock, this held variable here, it's a variable 0. If you have another thread actually looking at it, well, you might have, you know, it's the same example over and over again, which my x, which was incremented and decremented, here it's the same. So if actually there is a context switch in the middle, you might have a race condition. Okay, it's a chicken and egg problem here. We are trying to implement something to synchronize, and we have a race condition in the tool that we implement in our synchronization tool. Okay, so this is the naive approach, but there is still a problem. So here, what we do is the following. To implement that, we have 2 ways. Okay, the first way, for both of them, is going to be the hardware to the rescue, right? The first one is it's something we call there's a special instruction in the x86 called test and set. What test and set is going to do, it's actually going to it's one instruction where it's actually going to test a variable and then increment it. Okay, and in a nutshell, here I put some pseudocode, right? This is not this is nowhere implemented, right? But it's the logic kind of to understand test and set. Test and set is one instruction, but basically it does the following, right? You look at it stores the old value, and then turn this value to true, and then returns the old value. Okay, and it's going to do that in one instruction. And the good thing with that is, like, you know, what you can do is, like, here you can actually increment a value and check that the old version of the and test at the same time the old version of the value. So you see the if condition increment is all implemented in one instruction. And so because of that, actually, test and set is a good way to implement this kind of flags, right? Because here you can use it to actually do these kind of things here in one instruction. And in one instruction, you know you're not going to be interrupted in the middle of the instruction, right? The other one, so you can do that, right? You know, while test and set lock held, that's it. But it's a busy wait. You waste some CPU and it's unfair to access. The second one, and maybe here I'm going to stop. The second one, which is actually implemented in Pintos. Pintos doesn't use test and set. Linux does. But on Pintos, what they have done is, like, actually disabling interrupt just for the sake of the thing. Here, in a nutshell, you could implement it like that, right? When you acquire, you disable the interrupt. When you release, you enable the interrupts. But this is bad. Okay. Okay, I'm going to stop here. We're going to talk about that again later. If you are curious, look at the Pintos code and so on. Okay. If you have more questions about Pintos, I have office hours in 1 hour. At 2 p.m. I have office hours. Okay. All right. That's it. Have a good weekend. Good luck on the project. Start working on it. And talk to you next week then. Bye.